Hi there. Purpose of this video is to demonstrate how to analyze a production sample. In this example, 44 randomly selected oat bars of varying lengths. So what we're going to do, this is a sample. We're going to analyze the sample data set for mean and standard deviation, and we're going to compare it with an ideal quality process which has got its own mean and standard deviation. And we're going to conclude against a hypothesis test as to whether our sample is significantly different from our ideal mean. So we're going to use the null alternative hypothesis test with a 5% significance level. So a bit of background, basic statistics. The mean is the sum divided by the count. In this very quick example here, 15 data points, we add them all up. We get 330 divided by the number of samples gives us an average of 22. The average gives you some information, but it doesn't give you the spread of numbers around that mean. We're also going to, which the standard deviation value does, we're also going to use built-in Excel functions to process the data. Standard deviation on top of mean gives you an indication of how spread out the numbers are beyond the mean. Ideally, if standard deviation was 0, there'd be no spread of numbers. What we're looking at here is natural bell-shaped spreads, normal distributions. The higher the value of standard deviation, the more spread out the numbers are about a mean. What we're going to do is to calculate the mean of our sample data set. We're going to take each data point and subtract the mean. We're then going to square these differences. We're going to add up the 44 square differences, and then we're going to take the mean of them, which gives you your variance value, and then take the square root of the variance to get the standard deviation. Why do we square in here? We need to square because the difference from the mean for each data point could be plus and minus. And if we don't square the plus and minuses, we tend to cancel out and we wouldn't be able to extract information. What we expect to see if this is a normal distribution is the vast bulk of data points are within, for example, 95% around the plus and minus around the mean. So we would expect very few outliers. One standard deviation is 68% about the mean. Two standard deviations is 95%, and 95% is what we're looking at for our 5% significance. We want to see if there's any significant shift outside this 95% boundary for our 5% significance level. The normal bell-shaped probability density function, this curve, is defined by this complicated equation here. What's interesting, Euler's number comes up here again, E, which is 2.7182, which is a number that defines our reality. It's a natural process, so Euler's constant is in here again. We've also got pi in here. X is the data point. You subtract the mean, and then sigma here is the standard deviation. This is quite a complicated formula, so what we tend to do is rather than using this formula, we use the pre-calculated z-score tables. At any point, probability between two values is the area under a curve. What we're looking for here, we're going to do a test score in our Excel to compare the sample against the mean to decide analytically if it's significantly different from our ideal. So we're going to take the sample mean, subtract the ideal mean, and divide it by the sample standard deviation. Once we get to the answer to that in brackets, we multiply by the square root of the number of samples, which in this case is 44. And we're looking for this 5% significance level. So we're really looking to see whether our sample is significantly shifted from our ideal or not. What we'll do is use the z-score so that we can standardize the horizontal scale here within plus and minus 1, 2, 3, 4, 5 standard deviations about the mean, which has a z-score of 0. To work out the z-score, we take each of the data points, subtract the mean, and divide by the standard deviation. In summary, we use the z-score tables to avoid using this complicated formula. So what we're going to do is take the probability of the 5%, look up our z-score table, get a figure and compare it with our test score. So if we jump to the Excel, we've got our data sample here. There's 44 of them. I've numbered these lines, this column 1 to 24, sorry, 44. And we've got individual sample data points here. And what we've done is manually added them all up, not without using any Excel functions. We've manually added them all up. We've got a mean of 40.05. We've got our column here to get the difference from the mean. Then we've squared it in this column, added all up the sums, produced a variance number, and our standard deviation comes out to be 0.405. So this is our sample, and we want to compare it with the ideal. So what we're doing in this sheet here is just move this over. What we've got in here is I've started the data points at 38.0 length, millimeter length, to catch all possible outliers. So we're going between 38.0 and 42. And then for those data points, based on the ideal that's given in this table, and the idea is each individual learner gets a different ideal. So we use the norm.dis inbuilt function from Excel from the given mean and standard deviation because we want to plot it out. Then we've done the same using the built-in functions for our calculated sample mean and standard deviations. And what we can do is if we select those three columns together, what we can do is we can insert recommended charts and just a very, very, very quick visual check before we do the analytical approach. We can actually see that the blue one here is the ideal, and our sample does look like it's significantly shifted. Now, what we're going to do is we're going to do a test score calculation, and we're going to see that if it's shifted far enough to support our alternative hypothesis against the 5% significance level. The 5% is a fairly, it's a number that's chosen by consensus. The smaller the number of significance, then what you're more likely to do is to avoid any data sets that you're choosing and form conclusions just by a data set that's just got by random chance. So the smaller the significance level, then what you're really doing is you're making your test more rigorous. For this test here, we're using 5%. So what we've got here is we're creating a test statistic score. We take the sample mean and subtract the ideal, get an answer. And what I'm using for our ideal here is 39.8. We know that our sample comes out to be 40.05. Just looking at the numbers, there's not a huge difference in the actual number, but in terms of the standard deviation, it is quite significant. So we're going to do a test score, sample mean minus the ideal, get an answer. We then divide by the number of samples, which divide by the sample standard deviation to get an answer. And then we multiply by the square root of the sample size, which in this case is 44. That gives us a test score of 4.128. What we're then going to do is take that test score and we're going to compare it with our significance level. We're going to go to our z-score table. We'll take that out, that's been duplicated. So what will significance level 5%. This is a two-tailed test. So what we mean by that is we're looking for outliers up here and down here on the negative side. So it's a two-tailed test. We're looking either side. So we take our 5% and divide it by 2 to get plus or minus 2.5%. What we then do, that's the probability of the outliers. What we then do is look up the z-score table. What we're looking for is probabilities of 2.5%, which has a probability number as 0.025. which is that number there. If we match that up with a z-score in terms of standard deviations from the mean, we get 1.96. So there, minus 1.9, we go across, we go up there, we get the second decimal point, 1.96. And that is our 5% significance level translated to a standardized z-score. So if our test score number is less than 1.96, then what we are going to say is there's no significant difference from the mean. Now our test score number there is 4.128. So is our test score number less than 1.96? No, it's not less. It is significantly different. So what we can say there is we cannot support the null hypothesis. And what we're going to do is to support the alternative hypothesis to say that with 5% significance level, our sample is significantly different to the mean. We support the alternative hypothesis. If our test score number, if we want to make our test more rigorous and avoid any implications or conclusions from just random chance, we could use a 2% significance level, which would give plus or minus 1% for the two tails, either side of the mean in the standardization z-score table. So in that case, we wouldn't be looking at 0.025, we'd be looking at plus or minus 0.01. So if we go to this table, 0.01, 0.01, we're looking, we don't exact 0.01, but if we choose that one there, 0.0099, we then get a z-score of 2.33. If we dropped it down to 1% significance level, that's plus or minus 0.05. Now, again, if we look at this table here, we're really looking at that number there for probability, 0.0049, and we get a z-score of minus 2.58. And if we put this back into the sheet here, so for 5%, we're looking for a z-score number, a test score number to be less than our 1.96 z-score. And if it is less, there's no significant difference. In our case, there is. If we wanted to make our test more rigorous and avoid any issues with just random data sets, then we could reduce our significance level down to 2% and 1% and pick up our z-score tables against that probability. And you can see that the z-score numbers goes up if you lower the significance level. At the moment, we've chosen a significantly different sample size. If we happen to change that, just to show changing that data number there, if we change that to say take a different number where it actually takes 40.0 as the ideal and compare it against the sample, we then can see straight off visually without even doing the numbers that they're very, very similar here. So the mean looks almost identical. Just visually, you would see that there is no significant difference there. But if we go to our test score number, what we've now got is the Excel is automatically updated, and we now get a test score number that's only 0.855. So if we compare 0.855 with our z-score number 1.96, it is less. You can see 0.8 is less than 1.96 z-score. So we can conclude there is no significant difference from the mean, and we support, in this case, with our particular ideal against the sample, we do support the null hypothesis. So what we can say here is, in this particular case, we've got our ideal to be 40.0. The sample is 40.05. So what we can say is that it is not significantly different, and we can support the null hypothesis. So if this was actual quality process, what we're really looking for here is the ideal is zero standard deviation, but we're in the real world here. So what we can conclude, what we're really looking for is, yeah, if you reduce the significance number, then what you're really saying is your sample data set has to be more and more of an outlier to be considered as alternative. So what we're really doing in here is if our data set is our sample is significantly different, which you can see from that graph, then you would tend to support the alternative. So the best outcome in a quality process is to have very, very small standard deviation when all the data points equal the ideal. But in a physical real world manufacturing process, just variations and fluctuations in the machine performance, temperature, humidity, materials will tend to produce a normal distribution about a mean. And what we want to do is at regular intervals sample our production line to make sure our standard deviation number is not increasing, because if that number increases, it is indicating there's more variability in the process, there's some sort of degradation, and what you'll end up with is possibly just too much waste, because far too many data points are now beyond significantly out with the mean. Thank you for watching. I hope that's been informative for the two-tailed test. Please put any comments below.